Hello, my name is Hunter Levinson, and this is my Physics Lab 2 tape revisited report. The purpose of this lab is similar to the last lab, although now we're using the charge that we got from the last lab to determine the net electric field between the same two pieces of tape. And rather than modeling each piece of tape as a point charge, we're going to model it as a series of many, many charges. The equations that we're using are the same, although now we're adding the equation for the magnitude of the electrical field of a rod, which is equal to kq over r times the square root of r squared plus L over 2 squared, where L is the length of the rod. Our results were that the magnitude of E force and gravitational force were roughly similar at 5.438 times 10 to the negative third power. Our experiment remained the same, where we stripped a U-tape off of a base tape. And as you can recall from our previous lab, tapes A and B were attracted to the neutral hand and book. They were attracted to the negatively charged pen, and they were repelled by each other, meaning that both tapes A and B were positively charged. Our initial values remain roughly the same, where the tape mass is 0.002 kilograms, gravity remains 9.81 meters per second squared, and the displacement is 1 centimeter. Using these calculated tapes as point charges, we got that the Q value, the charge of each piece of tape, was 4.669 times 10 to the negative 9 coulombs. This was gotten using the assumptions that each U-tape had the same net charge, that electrons were evenly distributed throughout the tape, that all the surface area of the tape is affected by the charge, and for this calculation that the tape can be treated as a point charge. To find the net electrical force, we summed through all of the charges on the top piece of tape, and we looked at, for every single one of those charges on the top piece of tape, how was all the charges on the bottom piece of tape affecting it. So we had to calculate the electric field at every single charge on the bottom piece of tape at the location of every charge at the top piece of tape, multiplied by the charge of every charge on the top piece of tape. Assuming that the number of electrons was n is equal to 30, which would mean that I and j were also equal to 30, the magnitude of electric force, which is roughly the same as the gravitational force, was 5.438 times 10 to the negative third power. Our key assumptions for these calculations was that we could ignore air resistance, that the tape only consisted of n is equal to I and j charges, while there were probably roughly a million of electrons involved in this process, and that there were no other forces acting on the two pieces of tape. Script code is as shown below. This method right here determined the electric field at every single location of the top piece of tape given the bottom piece of tape. And this part right here was the summations where we determined the net force. And then we printed out the values below. These green arrows here represent the net electrical field at every single charge on the top piece of tape, while the white is the net electrical force on the top piece of tape, and the yellow is the magnitude of the gravitational force. As you can see, they're roughly the same. Our sources of error were that we assumed that the charges on the top tape did not affect the net force of the other charges on the top tape, even though this likely would have happened because all the electrons on the top tape were all of the same charge, so they likely would have repelled each other. And then similarly to the last lab, we assumed that charges were evenly distributed, while this was likely not the case because the tape was also attached to the two shelves, and the charge might have been interrupted during handling. If the tape had been treated as point charges, we could have used the force equation that F is equal to kq squared over r squared, which is equal to 1.962 times 10 to the negative third. And that is the same value that our code gave us when n was equal to 1 and 2. However, this value here slightly differs from when n is equal to 30 because having more charges creates a greater repulsion between the two pieces of tape. And our glow script code was likely more accurate because in reality, as I said, there's likely multiple million electrons that are affecting the second piece of tape.